Welcome back. So, in the last lecture I introduced the Black Scholes equation. I derived the Black Scholes partial differential equation by constructing a hedge portfolio in the continuous time version using a stochastic differential equation for the stock price, and then we also proceeded to solve the Black Scholes equations, and we arrived at explicit expressions for the value of a European call option. I now move to the next segment and that is the solution of the Black Scholes equation using the path integral approach. Path integral approach for the option valuation. Initially what I will do is I will take up the solution of the path of the option valuation problem using the path integral approach for a option which is path independent. In other words, the payoff of that option is independent of the path followed by the stock price. It depends purely and solely on the stock price or the value of the stock price at maturity. The payoff of the option is determined entirely by the value of the stock or the price of the stock on the date of maturity of the option. It is not related to, it is not dependent on how the stock reached that particular price, it is not dependent on the path followed by the stock in reaching that particular price. So, let us first attempt that problem, resolve that problem, and then we will move on to path dependent options. So, in a sense if you recapitulate the problem that we worked out yesterday or in the last lecture rather was the Black Scholes problem, that is essentially the path independent option, because European options are path independent. They are exercisable at a particular date, and the payoff on the option is dependent on the price that prevails on that particular date. So, Black Scholes option, as it is sometimes called, or the Black Scholes formula, relates to options that are path independent, whose payoff is dependent entirely on the value of the underlying asset or the price of the underlying asset on the date of maturity of the option. So, let us resolve or let us solve the Black Scholes option pricing problem using the path integral approach. So, as we did earlier, we can define the payoff at expiration of a Black Scholes option or a path independent option in terms of the expression that is given here in the green box. And you may note carefully that the payoff is defined only in terms of the price or the value of the underlying asset at maturity of the option, which is represented by capital T. F S T is a function of the terminal asset price S capital T. S capital T is the terminal asset price, the price of the asset on the date of maturity of the option. So, that is important. I reiterate that we are talking about options where the payoff is dependent on the price at maturity and the option is also exercisable on maturity. In other words, we are talking about European options number 1, and we are talking about options whose payoff depends only on the maturity value of the stock and is independent of the path followed by the stock price in reaching that maturity value. So, the Black Scholes partial differential equation can be written in the form, we have derived that equation in the last lecture, and it can be written in the form for the particular product or for the particular derivative that we are talking about. It can be written in the form given in the red box here, and in terms of the logarithm of the price, log of S, we can simplify this Black Scholes equation to the form that is accessible in the expressed in the green box here. Importantly, you may note that the important difference, the fundamental difference between the equation that is here in the red box and the equation that is here in the green box is that the coefficients are now independent of the independent variable in the in the equation that is here in the green box. They are independent of the x variable, the coefficients, as you can see, coefficient of this second derivative, second order derivative, first order derivative, and the term OF also, they are all independent of the variable x. So, that is a simplification that is achieved by transforming the independent variable from s to log of s, and of course, mu is equal to r minus sigma square upon 2, and the expression for OF also changes in conformity with the substitution of s as e to the power x. Now, this is a Cauchy problem, and the Feynman-Kac path integral formula provides a solution to this, and the solution to this, as in fact we noted when we worked out the solution for the option problem using the binomial model, this is precisely the same expression. If you note that, if you recall, this is precisely the expression that we arrived at using risk neutral probabilities when we did the option pricing in the binomial model. So, that is the formula that we have here for the option price. And the important thing to reiterate here is that Q is the risk neutral measure of probability, or the risk neutral probabilities as you may call them, or probabilities in the risk neutral world. And this particular average, that is the expectation value that we are talking about in the risk neutral world or with respect to the risk neutral probabilities, they can be represented as an integral over the set of all paths starting from the initial point at t, which is today when the stock price is s, to capital T, which is the maturity of the option when the stock price is s capital T, where s capital T is essentially a random variable, and it can take values, any value in the set between 0 to any real value between the set 0 to infinity. So, continuing from here, we have got this expression as the value of the contingent claim or the value of the option, and we represent it by a path integral in the form that is given in the green box here. And please note the substitutions: x is equal to log of s, and x t, that is the log of the stock price at maturity, log of s t is x t, and the path integral component, the prefactor represents the present value factor, the bringing back to t equal to this. See, the option is exercisable at a future date, and therefore, the payoff is going to materialize at a future date, and therefore, we need to when we work out the value as of today, we need to work out the bring back the expectation value to t equal to the present time, and this prefactor e to the power minus r tau does this job. It is the present value factor. It brings the expectation value of the option payoff to the date of valuation. The expression within the round bracket constitutes the path integral. The path integral which of the payoff over all paths between the initial or the current value of the stock and the projected and the value of the stock as on date of the maturity of the option, and then we are integrating this over with respect to dxt to cover all possible values of the stock between between 0 to infinity. Please note the stock value can take anything between 0 to infinity. Therefore, the log of st can take values between minus infinity and plus infinity, and therefore, because the variable here is log of st, that is xt, and therefore, xt can take values between minus infinity to plus infinity. The important term here is, if you note carefully, is the Black Scholes action A B S, which is this is the action functional. It is defined on paths as was the case in the case of quantum mechanics, and it is a time integral of the Black-Scholes Lagrangian function, where the Black-Scholes Lagrangian function is given by the expression here in the green box here. So, the action is the time integral of the Black-Scholes Lagrangian function as shown in the red box here, and the Lagrangian function or the Black-Scholes Lagrangian function is given by the expression in the green box here. Now, how to evaluate this path integral? We've got the expression for the path integral. How to evaluate this path integral? We use the standard mechanism of time slicing for this purpose. We have done it many times in this course in the context of statistics, in the context of quantum mechanics, again in the context of quantum field theory, and we repeat the exercise here again, and we discretize the timeline. We discretize the paths by discretizing the timeline. How do we discretize the timeline? As usual, we split up the time between the remaining time to maturity, that is time between t equal to small t to t equal to capital T. T equal to small t is today, is now the current instant, and t equal to capital T is the maturity of the option. So, this whole time interval between t equal to small t and t equal to capital T, which is represented by tau, is split up into n equal partitions or time steps, each of length delta t. They are all disjoint, of course, and therefore, they are bounded by n plus 1 equally spaced time points. And the ith time point is given by this expression here, and of course, delta t is given by capital T minus small t divided by n. The prices at each of these nodes or each of this in fact, see, we are now having a lattice, and the prices at each of these time points or lattice nodes on the timeline are expressed in terms of s of t I, and which is abbreviated as s of I, and the logarithm of the prices are expressed in terms of log of s I, which is abbreviated as, or which is symbolized by x of I. And now we talk about the discretization of the action variable or action functional. The action functional is now a function of n plus 1 variables starting from x0 which is x to xn, which is x capital T. This is the current point, x is the current logarithm of the current stock price, and x capital T is the logarithm of the stock price at maturity date of the option. So, and of course, there are n minus 1 other intermediate points at each of intermediate nodes on the timeline, at each of which the price is Si, and the logarithm of the price is log of Si, which is denoted by Xi. So, the action functional is a function of all these n plus 1 variables. Now, let us get the expression for the discretized action. We got the action for the Black-Scholes formula or the Black-Scholes from the Black-Scholes Lagrangian. The action for the Black-Scholes from the Black-Scholes Lagrangian takes the form which is given in the green box here on discretization, which is shown in the next slide. The Black-Scholes Lagrangian, as I mentioned earlier, is given by the expression in the red box here. When you simplify this, you get the second expression for the Black-Scholes Lagrangian, and therefore, the corresponding action, which is the time integral of the Lagrangian, is obtained as the expression that is given in the green box here. The last two terms are self-explanatory, they are quite elementary. The first term we come back to in the next slide. The first term A0 of x dash x of t dash is the integral of is the time integral of L0 of where L0 is the expression that is given in the red box here, 1 upon 2 sigma square x dot square. Now, what is this L0? L0 is the Lagrangian corresponding to the zero drift Brownian motion or zero drift process, which is given by the expression here dx is equal to sigma dz, or d, where dz is the infinitesimal Brownian motion increment, which we have been denoting so far by dw. So, dx is equal to sigma dz. This is a driftless Brownian motion, and the Lagrangian corresponding to this driftless Brownian motion is denoted by L0, and which takes the expression 1 upon 2 sigma square x dot square, which when we discretize this expression, we get the expression as you can see in the green box. The process of discretization is explained in the green box here, and the expression that we end up with is precisely what we have in the previous slide, which is by making these substitutions integral in these integral substitutions, the expression that we have here for A0 is I think we will have it in the next slide. I will come back to it in a minute. So, this is this substitution that we substitute the integral by the summation with the dt being substituted by delta t, x dot being substituted by xi plus 1 minus xi upon delta t. This is standard process, and that gives us on yes, here it is. I am sorry. Here it is. This is the this last term corresponds to the term that I have been talking about. This is the expression that we get from the action corresponding to the driftless Brownian motion or driftless Lagrangian. So, this let us call it the driftless action, and in this expression the last term we have obtained this expression by making the substitutions that are given here in the green box, and in using the expression for the Lagrangian, the driftless Lagrangian, which is given here in the red box. So, let me repeat, using the Lagrangian that is here in the red box and making the substitutions that are given in the green box, we arrive at the expression which is here in the green box here, the last term in the green box here, and we call this A0, which is the action corresponding to the driftless Lagrangian and the driftless Brownian motion, right. So, now we move to the path integral. When we do the path integral, we first simplify the path integral term. The path integral term is given by the expression in the green box here. Again, the viewers would be familiar with this expression. We have used it many times. This is simply extension of the path integral over the various paths which are denoted or which are obtained on the discretization or the time slicing and the corresponding slicing of the prices. Now, we have got some simplifications to do. Firstly, I reiterate, we are talking about or we are working on derivatives or working out the price of an option which is path independent. In other words, the payoff of the derivative is independent of the path followed by the stock, and therefore it depends only on the terminal price, and therefore it can be taken outside the path integral. And in other words, what I am trying to say is that f e x t can be taken outside the path integral, and another simplification can be done. The log price is x t. The path integral that we are interested in is with respect to the log prices x of t, and therefore we can take out all the other terms which do not involve x of t and from the action outside the path integral. In other words, we can from the path integral, or we can split the path integral into two parts. We can have a prefactor consisting, number 1, of the payoff of the option which is independent or which depends only on the terminal price, and number 2, other terms which do not relate to or which are not dependent on the prices or the log prices of the underlying asset. So, that being the case, we are able to simplify the action if you look at this action, the first term and the second term, both terms are independent of the prices x t, and therefore they can be taken into a prefactor. And similarly, we can take f of f e to the power x t also into the prefactor, and we can write the path integral as a separate quantity as k x t t subject to x comma t dxt, and where this term, the term in the green box here constitutes the path integral component. So, this is the path integral component, and all the rest of it is not related to the xt, the paths. It is not related to the path, and therefore, they have nothing to do with the path integral, and therefore, they can be taken as a prefactor. Now, what is this kxt? The kxt represents the transition probability density. It is the transition probability density of what? It is the transition probability density of the price to move, of the log price to move from x at time small t to x capital T at time capital T with respect to when the stock price follows, or when follows the stochastic differential equation, driftless stochastic differential equation, dx is equal to sigma dz. So, the stock follows this k represents the transition probability with respect to the zero drift Brownian motion with respect to the driftless Lagrangian, as we have just mentioned. So, and recall that the zero drift Lagrangian or the driftless Lagrangian is given by 1 upon 2 sigma square x dot square. So, we now evaluate this factor, and we will leave the other factors for the moment. We will leave them alone. We evaluate this factor. We for this purpose we write the action as A0, where A0 is the action corresponding to the driftless Lagrangian, the driftless Brownian motion, and it can be written in the form as I mentioned earlier. A0 takes the form expression given in the round brackets here, and so we have simply substituted the value of A0 here, and our next exercise is simply to simplify this particular integral. This integral is Gaussian, and we evaluate this integral using the formula that we have in the green box here. You would recall that we had used this formula earlier when we worked out the quantum mechanical path integral for a free particle. It follows absolutely the same lines, and the formula indeed used therein and here happens to be precisely the same. So, we quickly run through it. This integral of course is Gaussian. So, using this formula, using this identity, we can write this expression. If we pick up any two terms, if we pick up the two terms x2 minus x1 square plus x1 minus x0 square on the left hand side, if I take x as x2 and z as x1 and y as x0, and a and b both as 1 upon 2 sigma square delta t, and simplify the expressions, what I get is the result that is here in the green box. Now, it can be seen from this, if you look at this carefully, by using this formula, what has happened is this delta t has changed to 2 delta t here in the exponential as well as in the prefactor, and the second thing is the x2 minus x1 and x1 minus x0 have given us x2 minus x0. In other words, when we have integrated this with respect to x1, the x1 has gone out and we are left with x2 minus x0. So, I repeat, there have been two changes. Delta t has become 2 delta t in the prefactor, and in the exponential denominator of the exponential, and number 2, the x1 term has disappeared and we are left with x2 minus x0 squared, of course. So, now we again proceed the same way. We now pick up x3 and we evaluate the integral with respect to x2. We pick up the term involving x3 and we evaluate the integral over x2. The result would be that wherever 2 delta t appears, it would be replaced by 3 delta t, and at the same time instead of the x2 term would disappear and we would now have x3 minus x0 square. So, proceeding in this same way iteratively, we can do all the n minus 1 integrals that are there in this particular path integral. If you look at this, there are n minus 1 path n minus 1 integrals here. So, when we complete all the n minus 1 integrals, what we end up with will be number 1, delta t will become n delta t, and that is nothing but tau, because what is delta t? Delta t is equal to t minus tau upon n. So, n delta t is nothing but tau, and the squared expression that we will end up with is x capital T minus x 0 whole square, which will appear in the exponential. So, there is no dependence on n left after all the n minus 1 integrals are done. So, the limit n tending to infinity can be taken straight away, it is trivial, and the expression that we end up with is the expression that is given in the green box. So, this is the expression for the kernel that we have here, that we in the context of driftless Lagrangian. This corresponds to the driftless Lagrangian, please note this. So, it can be easily shown that the expression for k that we have obtained, k script that we have obtained, satisfies the diffusion equation with 0 drift, as you can see, which is there in the red box here, with the condition that at t equal to capital T, k x t will be equal to the Dirac delta function condition. This can be verified by solving the diffusion equation without drift in another manner, and then comparing the two results. We use the initial condition that we had postulated earlier, and that enables us to write the value of k as exponential of this operator into the Dirac delta function, as shown in the last equation here. So, this expression immediately is the immediate solution to the driftless diffusion equation given here in the middle of the slide. This can be easily verified by applying this operator and writing down delta in terms of its Fourier form or Fourier integral, and then applying this operator on the delta function written in terms of the Fourier integral, and then evaluating the Gaussian integral. We get the same result, we get the same expression for k as we obtained through the path integral formalism. We get precisely the same expression for the transition amplitudes as we obtained in the case of the path integral, precisely the same expression, and that shows that vindicates the veracity of the path integral approach. So, this is the evaluation of the integral Gaussian integral that is done in this particular slide. We have used this particular formula which is there in the green box. So, now we have to go back, because what we have done so far is we have obtained the green function or the transition amplitude or the transition probability in respect of the driftless Brownian motion. But remember, our stock price follows a Brownian motion or a stochastic differential equation with drift. So, we need to incorporate that the drift term also into our solution. Now, the green function for the diffusion with constant drift rate mu is obtained by multiplying the zero drift green function that we obtained right now, that is the transition amplitude. They are synonymous, the green transition amplitude or the green function by the drift dependent term. And this is easily seen. We have shown that OF is equal to the expression that is there on the right hand side. This is brought forward from earlier this expression. By the definition of green functions, we can write OF in the form which is given in the red box here. So, by comparing these two expressions, by comparing this expression which we have here in the red box and by comparing the expression which we have here, which we are brought forward from earlier, we get an expression for K mu. K mu is the transition amplitude corresponding to, or the green function corresponding to the Brownian motion with the drift coefficient of mu. So, that being the case, that is obtained as the expression which is here in the green box here. And when we substitute the expression for K, substitute the expression for the driftless green function K, we obtain the expression that is right at the bottom of your slide in the green box. So, it can easily be shown that K mu is the fundamental solution of the diffusion equation with drift, which is given here in the green box here. It is a straightforward exercise parallel to what we had done earlier in the case of the diffusion equation without drift, case of without drift. It is absolutely synonymous or absolutely similar. We can do it in the same way. Now, another important thing, the transition probability density or the transition amplitude also satisfies the Chapman-Kolmogorov equation, which also we had discussed at an earlier point in time. The semigroup property or the translation or semigroup or the property of Chapman-Kolmogorov equation, that is the probability of a particular state moving from state 1 to state 3 at time t equal t1 to time t3. If you intervene at a particular point in time t2 and you have you can integrate over time t2, integrate over all possible paths at time t2 that connect the state 1 to the states at time t2, and then from states t2 to the states at time t2 to state 3 at time t3, integrated over all possible states at time t2 will give you the transition probability of transition amplitude of moving from state 1 to state 3. So, this also shows that we can obtain the path integral by repeated application of the Chapman-Kolmogorov equation. You see, Chapman-Kolmogorov equation relates to one time slicing or one slice being introduced between T1 and T3, only one time slicing. Here we are having an infinite number of time slicings being introduced. So, it amounts to repeated applications of the Chapman-Kolmogorov equations. And from this expression which we have obtained earlier, when we substitute the expression for, when we substitute all the terms, we obtain the expression for path independent options in the form that is given here in the green box, and for a call option which in this expression simplifies to the expression that is given here on this slide. Thank you. We shall continue after the break.